Hello, everyone. I'm Shreyas Derashri. I'm the Vice President of Compute at Imagination. I'm responsible for Imagination's CPU, AI, and heterogeneous products and solutions. Today, I'm going to talk to you about the new era of compute that we have already entered. Like the laws of physics or thermodynamics, there are essentially three main laws that have guided us for 5 decades to predict the future of compute. The first, and probably the most well known, is Moore's Law. Rather than a law, it was an observation made by Gordon Moore in 1965 that the number of transistors would double every 2 years. We've been using this law to predict the compute performance for some time now, and that would translate to the compute performance doubling every 18 to 24 months. Now, one of the other things that has been added on to that law is doubling of the compute performance at a constant cost. So as you scale down the geometry, the cost remains the same. The next one is Dennard scaling. As the transistors get smaller, the power density stays constant, so that the power used stays in proportional with the area. Both voltage and current scale downwards with length. So as length decreases, the voltage and current can scale down. In other words, if the transistor density doubles, the power consumption stays the same. In theory, we can continue to increase the clock frequency, and we all know that clock is proportional to performance, so thereby increasing the performance. The last one is Amdahl's law. Amdahl's law deals with parallelism in computer architecture and gives us a formula for the performance boost of an algorithm, application, or a system if they were to run in parallel. Typically, every algorithm, application, or system has got some parallel and some sequential parts. And this actually limits the scaling in compute performance as we use more and more homogeneous parallel elements. Now, having understood the three laws of compute, let's have a look at the 50-year microprocessor trend data. So first and foremost, looking at this trend data, we know that Moore's law is slowing down. And note at what I mentioned about constant cost, lower nodes are becoming very expensive, and the rate at which the geometry was shrinking has slowed down significantly. The next is Dennard scaling. I think Dennard scaling ended in mid-2000 because of leakage and threshold voltages. Today, 4 GHz seems to be the maximal achievable frequency. And then we look at Amdahl's law, which deals with number of CPUs or cores in parallel. We all know putting more CPUs and more sequential elements no longer results in better performance scaling. There is always bottlenecks that creep in, particularly from the memory side or from other system elements. Having seen these challenges to these three laws of compute, let's see what is the demand for compute in the industry. We're just picking one example here, which is AI training. And you can see from the slide that up until 2010, there was a 2x scaling in the performance needs in the training algorithms around the world. But since 2010, clearly there has been a 10x per year demand increase in the compute performance. So where does it leave us? On one hand, our three main governing laws around compute are either slowing down or have stopped. And on the other hand, we have a world where the compute needs are increasing way faster than what typically the three laws could deliver us. Where do we go from there? We don't have to look far. We just look at the nature. And the most efficient compute machine on Earth is the human brain. So how is it organized? It's an heterogeneous architecture. We have parts of our brain that deal effectively with vision types of use cases, parts of our brain that deal with audio, and then parts of our brain that deal with memory functions. Basically, what I'm trying to tell you is that if you have different types of use cases, you need different elements, compute elements in the system. And that's what the human brain is telling us. Let's take a real world example and let's look at the future of automotive architecture and the compute needs as they are evolving in the automotive sector. From an architectural point of view, there is a consolidation of ECUs, domain controllers, and into zone controllers. The architecture is moving from a very distributed compute architecture to a centralized compute architecture. In addition to that, the compute needs are growing at a phenomenal rate in this industry, right from digital cockpits up to ADAS and autonomy, where autonomous cars, robotaxis are coming to the market. There are more sensors in the car and more processing. The compute demands are over 2000 TOPS per 50 watt in an autonomous robotaxi use case. On top of that, there is huge complexity of software that needs to be developed and run on these complex heterogeneous machines. Let's look a bit deeper on the autonomous use case. Now here, we have shown a typical autonomous robotaxi use case, a pipeline of such a platform. You have sensing that comes from cameras, lidars, radars, and ultrasonics. Then you have algorithms that deal with perceive and localize. You have algorithms that do scene representation, algorithms that look at planning and path prediction, and then you have control algorithms that deal with uh, the nature of the car, the velocity, the steering, the braking, and acceleration. All of these different compute needs have got require different compute architectures. Sensing, which is typically more signal processing, requires a mix of DSP and floating point functions. Uh, Perceive and localize is more moving towards machine learning, artificial intelligence based algorithms, and so is path planning, planning and decision. Control is typically dealt with elements which are more sequential. That gives us an idea of the complexity of the algorithms that would be running on a future car. And a single compute element cannot be used to accelerate all of these different types of algorithms. So typically in a automotive SoC, you have application processors, you have real-time processors, you have AI accelerators, you have GPUs doing computes, you have GPU doing graphics, and then you have safety elements, safety islands, and connectivity logic. What we are saying is that the future of compute is heterogeneous compute, and these elements like the CPUs, AI accelerators, and GPUs will be working in a more heterogeneous formation, working and addressing the different needs of this market. So we believe the future is heterogeneous. In fact, the future is not just heterogeneous, the future is efficient heterogeneous. There's a trivia that I just wanted to share with you here that by 2030, 21% of the total world energy will be consumed by things like data center, consumer devices, networking, and the internet. 21% of the total world energy. Add to that the, 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 the electrification of our vehicles. The future is definitely heterogeneous, but it is efficient heterogeneous. So what does it take to build a heterogeneous system of tomorrow? There are three key ingredients. The first and foremost is the compute element itself. The compute element can be a CPU, which deals with sequential compute workloads, can be a GPU that deals with parallel floating point compute workloads, or can be an AI accelerator that is there to run very, very fast neural networks and do deep computations around AI and machine learning. That's one element of or one ingredient of a heterogeneous system of tomorrow. The second is the fabric or the mechanism for an effective data transfer between these elements. And the third, which is probably very, very important, is the software tools and frameworks that glue all this together. In essence, the data bottlenecks have to be resolved as system scales. Memory and cache architecture has to be optimized. All of that has to be done with safety and security in mind. And last but not the least is you have to deliver a programming model of such a complex system, which is heterogeneous in nature, but looks homogeneous from a software point of view. We at Imagination are working to bring this future together. Our portfolio of IPs consists CPUs, GPUs, AI accelerators, as well as connectivity IP. Very recently, we started to develop our RISC-V based CPU to complete this story. Why RISC-V CPUs? I think RISC-V CPUs are at the heart of heterogeneous system of tomorrow. RISC-V architecture ISI itself is democratizing and accelerating the compute of the future. There are various interesting elements that make RISC-V very, very compelling. The first and foremost, it's a foundation based in Switzerland. It's non-profit, neutral to geopolitical challenges. It's not led by one company. It's driven by contribution of members. And as of today, there are over 2,000 members in this ecosystem. It's a modern ISA. It's built on 30 years of understanding or know-how of RISC architectures. And it's a modern, scalable architecture for next generation AI, ML, heterogeneous compute applications. Through its unique custom extension, you can make it very use case specific, thereby solving very specific challenges in your particular industries. And of course, it's got a huge traction in the academic world. There is a lot of software support around Linux, tool chains. So the ecosystem is all coming together. So as we bring the heterogeneous future together, one may ask, why RISC-V CPUs from imagination? And there are 5 main pillars to that. First and foremost, Imagination is the most established IP company to enter RISC-V. We have a proven track record of over 2.5 decades of developing, delivering, and supporting complex solutions. Our CPUs are actually silicon proven. Some of our initial microcontroller CPU RISC-V based CPUs are already shipping in automotive GPUs. Third, we have the complementary IP in-house to make a compelling heterogeneous compute solution. So we have the GPUs, the AI accelerators, and we are bringing it all together around the RISC-V CPU. Because we are a company which has supported our customers for over 2.5 decades, we have a very, very strong worldwide support team that ensures that our customers get their SOCs right the first time. And lastly, not very well known, Imagination, through its previous ownership of MIPS and its Meta CPUs, has got access rights to over 850 fundamental CPU patents that give our customers the right peace of mind as they bring their products to the market. So what's our direction of travel? We just released our 32-bit in-order real-time embedded processor. Next, we are working on our 32-bit and 64-bit multi-core embedded processors with vector support, followed very closely by application cores, then following them up with high-end out-of-order cores. All of these CPUs work with our AI and GPU IP to create heterogeneous solutions, but we are also working on the next generation heterogeneous compute solutions, bringing all these IPs together to deliver a disruption in compute performance. All of our IP is developed as per the stringent ISO 26262 automotive systematic development requirements. We have ASA certification throughout the design, specifically for the automotive use cases. And we are also looking at end-to-end security in our heterogeneous solutions. Like I mentioned in the slide before, we introduced our first product to the market at Embedded World earlier this year. That is RTXM 2200. We believe, based on the publicly available data, RTXM 2200 is the highest performance density CPU in the market today for the like-for-like CPUs in the market. It's a highly configurable design, flexible for multiple use cases. It's built to the industry's highest quality standards. One thing we are very proud about and stand behind is the quality of the CPUs that we are developing. And last but not the least, it's designed to enable market-leading heterogeneous solutions. The RTXM 2200 is an in-order dual-issue 11-stage 32-bit real-time processor. It implements ratified extensions like the iMac, ZICSR, ZIFNC, but it also includes optional floating point and bit manipulation extensions, and an optional bfloat16 for AI ML type use cases. The IP itself is highly customizable, whereby you can add or remove the extensions. You can configure the cache sizes, the TCM sizes, the tightly coupled memory sizes, and the PMA regions. You can also optionally remove the debug and trigger and trace from your end product. From the CPU side, we are not just giving the IP. We have a complete solution. The Catapult RTXM 2200 comes along with Catapult SDK and Catapult Studio. Catapult SDK is our SDK that delivers software support for FreeRTOS with the first core, and as and when the application cores would be available, we will provide support for Linux and other rich OSs as well. The SDK is fully compatible with industry standard tools, including GCC LLVM and GDB debugger. We are focusing on optimizing the LLVM compilers, thereby delivering much higher performance from a standard implementation available in open source. Our Catapult Studio, our IDE, is actually very unique. It's based on Visual Studio Code, unlike the other IDEs which are based on Eclipse. It empowers developers to take full advantage of the Catapult CPU. It offers enhanced debugging and visualization capabilities. It's available on Windows, Ubuntu, CentOS, and macOS, thereby delivering developers a delightful experience of using our IDE. So that is what we are offering with our first product and with our CPU products. My last slide gives you a peek into the future that we are working towards. The heterogeneous products of the future, where we are bringing along different configurations of CPUs, neural network, AI accelerators, different GPUs, connected with efficient data sharing between them on the hardware side. But on top of that, we're also looking at the programmer's model and ensuring that the IP is very easy to be deployed in actual use cases. So we are also providing a full compute stack, particularly for the AI use cases, but also libraries for the non-AI signal processing use cases. And they will be supporting our NNAs, our AI accelerators, our CPUs, and our GPUs. So that's what imagination is doing for the next era of compute. Thank you.